We've got quite the lesson for you all, advanced Earth space intro physics people. I say that with a little bit of sarcasm for sure, because I think, correct me if I'm wrong, you know that the Earth does this.
Yeah.
Oh my God.
Right? Okay.
It's so cool.
The Earth rotates on its... It's called the axis of rotation, for crying out loud, right? Okay. So we got that. Can we learn anything from this lesson? Maybe a couple of things. So pay attention, have your notes out, ready to put it down. If it's already in your forehead, don't put it in your notes. If it's not in your forehead, put it in your notes. Hey guys, the Earth's rotation makes it so that we have sunrises and noontime and sunsets and nighttime. Okay, it's wonderful.
Wow.
How do you know it rotates? Oh my heavens. Okay, so as we just said, we've got a little bit of a clue. Earth's axis of rotation, that imaginary line running from the geographic North Pole, that is the center of rotation there, the North and South Pole, right? That line that runs between those two, that's the axis. And did you know that it's tilted?
Yes.
I reckon.
In relation to our the elliptical plane that we orbit the sun in relation to that plane, the planet Earth is tilted a little bit. Here it's got tilted the other way, whatever. Also, it rotates in a particular direction. If you were to look at it from above the North Pole, it rotates counterclockwise. Okay, put that in your notes too. If it's not in your forehead already, it rotates counterclockwise. And that makes sense because that means it's spinning towards the what direction? Northeast, southwest? It spins toward the east, right? Which is why the sun rises in the east and it sets in the west. Just like, by the way, all the other stars and planets and whatever that we can see at nighttime, right? And things appear to go across the sky from east to west. All right. So there's that thing and stuff. Moving on. Rotation. Day-night cycle. All, of course, caused by the rotation of the Earth. Day-night cycle takes how long? 24 hours. It's almost like you've been around a minute. Very good. As ninth graders, I'm very proud that you knew that. But sometimes the day part of the day-night cycle is longer, and sometimes it's shorter. Right now, the day part of the day-night cycle is getting shorter. It will be the shortest when? Winter solstice. The equinoxes, I guess, is that plural? Would be the spring and fall, right? That's when you have the equal amount of day and nighttime hours. The winter solstice is the shortest daylight hours of the year, which is nice because after Christmas, right around Christmas and after, the days start to get longer again.
Is that why we do time changes?
Yeah, it has to do with that. A lot of it's just trying to keep the time of day where, like with this, I don't even know anymore. I wish we'd stop it. Anybody else tired of the shifting of the clock? Spring forward and fall back. Whatever the reason was, I don't care. I don't care if it gets disproportionately earlier or later with the sun. I think it had something to do with making more work hours, but that was like before electricity gave us the light bulb for farming purposes. Yeah, we're good. The tractor's got a set of headlights now. We're okay. Yes.
Isn't there like there's like a time where it's like 2 weeks or something?
Oh, not just Canada. Okay, so the question was, isn't there a place in Canada where it's always dark? Or is there a place where it's always light? So you guys know the Arctic. Okay, so if you look at a map or a globe, there's an Arctic and an Antarctic circle. The Arctic circle, I believe, it's not even on here. It runs really close to Iceland. I think it actually clips a part of Iceland. So if you're north of that Arctic Circle or south of the Antarctic Circle, there will be at least a couple of days in the winter where it will be dark all day. Now, you might, if you're really close to the Arctic Circle, you might, but just on the north side of the Arctic Circle, you might like, oh, the horizon's getting bright, the sun's about to come up, and then it just never does. Then it gets dark again. Does that make sense? Same thing in the summer, though. In the summer, like the sun's going down, it's going to set, it just never quite sets, and then it goes back up. Does that make sense? So, anybody baseball people? Got one? Just one? Two. Okay. Got two baseball people. Other people know what baseball is. Yes? Okay. So there are tournaments that they play 24 hours. They can play all day long in Alaska because the sun never goes down. For a few days a year, they have this tournament thing up there, and they can just play. It messes with people's sleep cycles though too, because it doesn't go. So they have to have like those dark blackout curtains or whatever on their window. You guys know what I'm talking about? Yes. Solstice. Gosh, how do you spell solstice? Solstice?
Yeah.
Is that right?
Yeah.
That doesn't look right?
It's right.
Google it.
You can check it. Fact check me. Spell check me. All right. Shh. Moving on. I think we're ready to move on. 24. All right, summary. So again, with the summaries in CK12, if it's in your forehead, you're good. If it's not in your forehead, you better put it in your notes. Sun, moon, and stars appear to travel from east to west across the sky each day. Earth rotates once every 24 hours, and it causes the day-night cycle. This is high-level stuff. I feel like this is ridiculous. It's written for middle schoolers. Like, I mean, I guess people don't know it by 6th grade, but I feel like they should. What?
Another like really random question is: does it take exactly 24 hours, or is it like milliseconds?
It's going to be very close to it. Yeah, very close to it. All right, you could look that up too, because sure. Why? Why does the Earth spin? Anybody know? Gravity of the moon. Actually, the gravity of the moon is like trying to stop us from spinning, which we'll learn about here. So let's watch.
23 hours, 56 minutes, and 4 seconds.
Did everybody hear that? He's fact checked it. The Earth's day is 23 hours, 56 minutes, and what?
4 seconds.
4 seconds. Okay, cool. Here we go. Sorry, I can't full screen it.
Hi, it's Casey Gardner, and this year on Tell Me Why, we're going to find out why the Earth spins. So I'm at NASA with Dr. David Bergenkamp for the answer. So why does the Earth spin?
Well, the story of the Earth spin goes back all the way to the origin of the solar system, 4.5 billion years ago. The solar system started out as a cloud of gas and dust. And this gas and dust clumped together to form the sun and the various planets. And the way
Whoa. He said in space there was a cloud of gas and dust. What do we call that? A what? A nebula. Like the blue gal from Guardians of the Galaxy, right? Okay. All right, here we go.
the Earth grew was to cannibalize smaller clumps.
Whoa. So we've got clumps of dust then, and then the bigger pieces start to, he used the word cannibalize, is like gobble up others. Somebody threw out the word, what's that called? Starts with an A. Accumulation, or the fancy word we had on the board? Accretion. Good, accretion. So the cloud of gas and dust, you start to get some rotation. We call it an accretion disk. So what they're showing right there actually is an animation of an accretion disk. And at the center is where you have the most mass concentrated. That's going to become the sun, whatever star forms in that center of mass. And then outside of that, if you have debris of the right type, you can form planets out of that. And then, of course, you'd have leftover stuff like the asteroids and whatnot. Yes? So because the rotation is like this, the centrifugal right, force kind of squeezes it into a disc shape, that outward force. The gravity force is the centripetal force holding it in. The rotational force pulls it out. Does that make sense? So that flattens the disk, flattens the cloud into a disk. That's better. Yeah.
So if we spun fast enough, would we actually be able to
Yeah. Yeah. If Earth spun fast enough, I suppose. Remember the other video? They had the analogy of pizza dough, and you throw it up and you spin it, and it gets flatter and flatter and thinner, right? So yeah, I guess if you spun the Earth fast enough, it would have to be it'd have to be crazy fast to counteract, because Earth is so massive. It's got a lot of gravity to hold it in the round shape. But we do have a bulge, don't we, at the equator? Aren't we a little bit flattened because of that centrifugal force? Didn't we talk about that? Absolutely. Good. All right.
Also growing. So if you were sitting on the surface of the Earth, you would see a bombardment of particles all the way from dust particles to perhaps Mars-sized objects. And it turns out it's this bombardment which also gave the Earth its spin. The Earth is sitting out in space, bombarded by all these particles. It's going to have some rotation. So that's where the rotation of the Earth comes from. But that's not the end of the story. It turns out in the early days, the Earth was rotating much faster than it is now. So it was perhaps rotating 5 times faster. So the question is, why has it slowed down? Yeah. And it turns out the main culprit is the moon. The moon raises tides on the Earth. And it turns out that the moon attracts the ocean tides. And it attracts them in such a way that the gravity of the moon tries to stop the Earth in its rotation.
It's called gravitational friction or drag. So the Earth is spinning, but over here we've got this massive object called the moon, and it's pulling in one direction. Now it's also traveling around the Earth as it's doing so. The moon's gravity is pulling on all of the Earth, yes? But what can it affect more, solid objects or liquid? Okay. Or fluid, to be more precise, because not only does it cause tides on the oceans, right? It actually, it creates a bulge, right? It actually can pull on the atmosphere a little bit too, right? So you have a bulge, the liquids, the fluids of the Earth pull towards the Earth's side, or towards the moon's side. So as the moon orbits, the tide follows the moon. Does that make sense? So some of the water from this side gets thinned out and it gets thicker on this side. So if you are at a high tide, the moon is where? It's on your side of the Earth. If it's low tide, it's on the other side of the Earth. It's pulling water away from your side. Does that make sense? Now the effect on the liquid, I think, would be more than the atmosphere. I'd have to look that up. Interesting. I hadn't thought of that before. Yes?
What causes like what we see at night? Like what, like for example, like either we see a full moon or crescent moon.
Whether it's a full moon or a crescent, we'll talk about the phases of the moon too, I think, this year. You should cover that in the 6th grade too. So it's where it is in orbit around us. So in other words, so from our perspective, is the sun over there? If we're the Earth and this is the moon and the sun's over there, we would see part of the sun side of the moon and we'd see part of the dark side of the moon, the shaded side, right? So you'd see like a half moon. But if the moon were over here, if the sun was over there, the moon's over here, we'd see nothing but the lit side of the moon, correct? So you'd see a full moon. If the moon, if the sun's over there and the moon's over, wait, what did I say the sun was over there? I get confusing myself. If the moon and the sun are on the same side, the lit side would be on the other side. We would be seeing the shaded side of the moon. So that would be the new moon. Does that make sense? So that's where the phases come from. It's the position of the moon in its orbit around us in relation to the position of the moon, of the sun. Goodness. Okay.
Well, this is a very
That's the first time I got that question today. So I had to actually use my noggin.
place effect because the tides aren't very high and the moon is very far away, so its gravity is weak. But this effect keeps on going on century after century, and it's been doing that for billions of years. Originally, the Earth started out rotating much faster, and now it's slowed down quite a bit. The Earth will continue to slow its rotation in the future. What's peculiar is that the moon will move away from the Earth for a while, the moon will start coming back in towards the Earth, and eventually it will collide with the Earth.
I don't think I had heard that before. Basically, I had understood that the moon is the gravitational drag and all that. It's drifting away. I hadn't heard that the moon would become a boomerang. Right? Kind of goes out and comes back like a boomerang. Back to the tides. Just another thought I wanted to share, make sure I got across. If the moon's over here pulling on the earth and its oceans, causing a high tide, what if the sun was on the same side? So if the moon's here, the sun's over there. That wouldn't equal out, it would magnify the tides. So if the moon and the sun are on the same side of the earth, the tides will be at their highest. Okay? If they're on opposite sides, then they would partially cancel out. You'd still have a high tide, but it wouldn't be as high. Does that make sense? Yeah.
So before the moon would ever be able to crash into the earth, the sun.
I cut him off before he finished. Yeah, he says it's not going to happen for billions of years. So about the time the moon would be coming back on a collision course, the sun would also be like expanding, becoming a red giant. So it's just not be a good time to be on planet Earth. So make plans now. Okay, make a reservation to get out of Dodge. Yeah, we'll be out of here already. Billions, yeah.
So then, with that logic, with like the moon slowing us down, is there a point that we would completely stop rotating?
It will be slowed. I don't know if it would ever stop. And then remember this, guys. Remember he mentioned that collisions can increase or decrease, right? So if we were hit by something, it can, if we're spinning this way and we're hit at the right angle, it could accelerate that speed, right? If we're hit the opposite way, it could decelerate that. If we're hit at a weird angle like this, couldn't it change our tilt? Of course, sure. But those are all what ifs in the far distant future. They've got pretty good modeling to extrapolate out for decades, right? But can they make predictions centuries? Yes. Maybe thousands of years? Yes. But there's always the things that are unpredictable. What if something else came into our system that we didn't see coming, right? There's things that you can put in your models, but those are known knowns. And then there are known unknowns, and there are unknown unknowns. The unknown unknowns are the scariest ones. Yes. Did that just confuse the heck out of you? Do I need to say that? Oh, yeah, let me back up. Her face is like, what are you talking about? There was, I forget who said it. Probably more than one person, but I think Donald Rumsfeld got credit for it. He was DOD secretary, I think, back like the early Bush years. There are things that you know. And you can put that in your modeling, right? I know this. And then there are things that you don't know. Are there some things that you don't know yet? Okay.
Yeah.
But you know that you could know them someday.
Yeah.
Okay. Are there things that you might know someday, you don't know now, but you don't know what those are?
Yes.
So those are the unknown unknowns.
Oh.
Those are really tricky. Those come at you. You didn't even know they were coming. It could be good, could be bad. What's up?
So, I guess kind of read a question too. What do you think would happen to humans if the rotation became longer or shorter?
So longer days, I don't know what effect that would have on nature. The change would happen so slowly that the natural world would be able to adapt to it.
I think we would have to work more or something.
I'd say a longer day, hypothetically, would mean I could get more work done in a single day, but wouldn't the total amount of time be the same? We would just be dividing it differently. Okay. Are we on to our next lesson? We are. Let's go to our next lesson. So again, spoiler alert, shocking news, the Earth goes around the sun.
Oh, that's why we get leap years, because it's
We're going to do the questions. I'm combining these two because they're mostly what you already know. We're adding a little flavor, a little spice to it, but mostly you already know. Yes. Yeah, take a pass. All right. So Earth's revolutions. We revolve around the sun. And this is Pluto, right?
No, that's Jupiter.
She got upset. Yeah, it's Jupiter. What's this? The great red spot. Okay, that's a highly scientific term right there. Whoever named that, they really had their thinking cap on. What's this? I think that's supposed to be a moon. Looks like a bubble. What's this? That's a moon. What's this thing here?
A moon.
That's a moon passing in front of, yeah. So why does it look black like that? Because the reflection, the light reflecting off Jupiter, this is on the dark side of the moon. Cool, right?
Wow.
All right. What kind of revolutions are we talking about? Not the political kind. But if you think about the word revolution, no matter what the case, you should be thinking about change. Okay, and our revolution around the sun causes change. Extra conversations, if it's about this, I'm fine with it, but keep it quick and to the point. Copernicus, and what's his first name?
Nicholas.
Nicholas Copernicus. I love it's got a good ring to it, doesn't it? He changed how we think about our solar system. Previous to Nicholas Copernicus, most people were like, the Earth is the center. The center. No, they knew it was round, but they thought the other stuff went around the Earth. They didn't think it was the sun. They just thought that it was the center of the model that they had come up with. So, what's that model called?
I was just going to look that up.
Heliocentric
to the sun.
Heliocentric is the sun. What is Earth? So helio means to do with the sun. Starts with a G. Geocentric is Earth. So they believed in the geocentric model. And Copernicus says, no, I've got this idea here. Heliocentric's the way to go. Galileo then used his upgraded telescope. So Galileo gets credit for inventing the telescope from a lot of folks. Did he invent the telescope? Well, he invented a telescope. So there was already the idea out there of optics to magnify. He just improved upon it. So he invented a improved telescope. And he found what became known as the Galilean moons around Jupiter. Yes, please. So the Galilean moons orbit what? They orbit Jupiter. So he sees, where are we playing a game? Okay. So he sees these moons orbiting Jupiter. And he says, well, or he thinks rather, if we've got these moons orbiting a planet, does it stand to reason that a planet could orbit a larger body too, like a star? So that's one of the pieces of evidence they use to argue that, okay? Earth orbits a star. We call it the sun. Shocking. Takes 365.24 days. That's why we get leap year. That's right. So 0.24 is awfully close to a quarter, right?
Yep.
So 4 quarters makes in this case, a whole day. So February 28th, but then every 4 years we get a
February 29th.
February 29th. What?
Isn't there like a year you skip like year it's
So 3 years in a row. 3 years in a row, you would have 28 days in February, and then every 4th you get 29. What were you going to say?
like every 1,000 years, it's like they skip it. It's like it adds up between that 0.4.
Oh, okay. Every 100 years we do something different?
Yeah.
You got me beat on knowledge on that one. I'll have to look that up later. So I'd have to look that up. So, okay, cool, because it's probably still not quite perfect. Okay. Okay. That makes sense. Yes. Sure. Why is that? I don't know.
Look it up.
So you asked, why so few? Why don't we just peel a day off of one of the months that have 31?
Yeah, make more.
Right, and give that to February? I don't know. Whoever was responsible for creating the months, I guess. I don't know. Guys, I don't know everything. All right. Earth's orbit. If this isn't in your forehead, put it on your notes. The Earth isn't a perfect sphere. It is a oblate spheroid. And similarly, the orbit is not a perfect circle. It is an ellipse. We have an elliptical orbit. All right. It says here that sometimes students think that slightly elliptical or oval shape means that, oh, well, when we're closer to the sun, it gets warmer. When we're further away from the sun, we get cooler. And that's what causes the seasons. No. But interestingly enough, we have had times in Earth's past where it was more highly elliptical and it would have impacted at least some. And right now, planet Pluto, for example, has a very highly elliptical orbit. Remember I said it dips inside of Neptune's orbit sometimes? Okay. So on Pluto, in winter, it's the furthest out, right? So Pluto actually spends most of its time, one of Kepler's laws, it spends most of its time traveling more slowly further away from the sun. So it spends more time in winter. Winter on Pluto is so cold that any gases that would be in its atmosphere, most of them are frozen out. They actually fall to the ground. And then in summer, it comes in so much closer that some of those gases will actually evaporate. They'll thaw out and they'll be going back into the atmosphere. So the atmosphere gets bigger. Does that make sense? So images of Pluto, if you can get them, if you got close enough or have good enough optics, you know how atmospheres kind of look fuzzy in pictures through optics? Pluto will look clearer in winter because it has less atmosphere, and fuzzier in summer because it has more atmosphere. Cool. Anywho, distance. Write this in your notes if you don't have it in your forehead. You probably don't have this one in your forehead. 93 million miles Earth to sun distance, or like an AKA, also known as 150 million kilometers, or AKA, also known as 1 AU. An AU is a what? Astronomical unit. Very good. So an astronomical unit is an AU. One. That's what the definition is. The distance, the average distance from Earth to Sun is 1 AU. And that's useful for measuring distances to further out objects in our solar system. So like Jupiter might be, I'd have to look it up, what, 5, 6 AU? I don't know. Somebody Google that for me. How many AUs is Jupiter from the Sun? Oh, hey, I wasn't too far off. 5.2 AU from the Sun to Jupiter. So it's only about 4 AUs from Earth. 4.2. Cool. Also, it says the Earth's speed in orbit, rotational revolution speed, whatever, how fast we're going around the sun is 17 miles per second. Go ahead and put that in a calculator. A mathemator, a number cruncher machine, Numbermatic 2000, convert it to miles per hour. How would you go from miles per second to miles per hour? Times 60 and times 60 again. To go from seconds to minutes and minutes to hours. Somebody, once you got it, tell me. You got it?
I have a different thing that I learned.
Oh, okay.
I'll tell you.
Wait, what?
17 miles per second. So 17 times 60 will get you miles per minute. Times 60 again will get you miles per hour. Yes?
61,000.
61,200 miles per hour in our trip around the sun. We is scooting. Is that fast?
Yes.
That's ridiculously fast. Yes, it's fast. My memory. I'm wanting to say the Dawn Horizons spacecraft that went out to Pluto moved at like half that speed. Google it, fact check me. How fast did the Dawn New Horizons spacecraft travel? How fast did it go? Dawn, I think it was called the Dawn spacecraft, but it was a New Horizons mission. What?
36,400 miles.
Okay, so like half the speed. It was a little over half the speed. So our fastest spacecraft at that time, at least, 36,000 miles per hour, and the Earth almost doubles that. We scoot, yes.
Are we to go fast enough
No. Well, I mean, if it goes fast, I suppose there'd be a limit at some point where you would feel it. The problem is not problem. The good thing is that Earth's gravity is sufficient that we don't feel the movement at all, do we? It's all about senses and perspective. Have you heard that before? It's about relative speed. We're moving at the same speed in relation to things that we can actually see, feel, touch, hear. So we don't experience the sensation that we're moving at all. It's just like if you're on a train or in a bus or something, and as long as the road's smooth, you wouldn't, if you're just like, especially if it's at night, no lights outside, you wouldn't see anything moving, right? So, and everybody else in the bus is moving with you in the same speed, the bus itself. So you don't feel a sensation of movement. Okay, you're moving, but you don't feel it. Yes. Mm-hmm.
Can you see us moving? Can you see?
The movement is slow. So, for example, over the course of the night, you could track a planet or a constellation or whatever. You can track it moving across the sky. So, yes, you can see the movement. But that movement is caused by Earth's rotation, not by the movement of the planet. So, from night to night, you can track, has it moved? So, the same time of night, has it moved in relation to the last time you observed it? So, when you're talking about astronomical observations, you have to track for weeks or months. Does that make sense? To see if something has actually moved. Yeah.
I figured out why February has 28 days.
You did? Tell us why February has 28 days.
Because of an early Roman calendar reformed by King, I don't know how to say his name, who established the 12-month calendar, and due to Roman suspicious, designated with the least auspicious month, February, which honored death and was associated with rituals of purification to hold the unlucky even number of days.
So there's some superstition involved.
Yeah, basically.
And blame the Romans. Basically, they established a 12-month calendar. There was some superstition involved, and they made it the shortest month because it was unlucky. So you wanted to spend
made it 28 to them was unlucky, so it gave it 28.
Okay, cool. Very neat. Learn something new every day.
I tried to read this.
You have copy of this? Is that what you saw?
Yeah. Okay. Yes.
This is like from earlier, but this says that a sidereal day is how long it takes the Earth to spin once relative to distant stars. Which is 23 hours and 56 minutes.
Sidereal?
Yeah.
Okay.
And then a solar day is how long it takes for the sun to appear in the same spot in the sky.
Okay, so there's two definitions of a day.
Yeah.
Earth spinning in relation to the interstellar neighborhood, right? Or Earth's rotation relative to the sun. Because the solar one would be less?
Yeah. No.
Or more?
Solar day
Okay.
is 24.
Because as you're going around, it would take a little bit more than a day to be directly facing the sun again. Okay. Cool. Summary, and then we're going to watch the video. If it's not in your forehead, put it in your notes. Earth's orbit around the sun is somewhat elliptical. Earth's seasons are not caused by the shape of its orbit. Earth and the other planets of the solar system revolve around the sun. And we're going to watch this video, and it will fill in a little bit more details about the seasons. Yes.
Ain't the seasons caused by like the Earth's
tilt? Yes. The amount of radiation being able to be absorbed.
Yeah, by the sun.
Yeah.
So.
Well, by the Earth from the sun. Yeah. Yes. No, because I want you to pay attention to the video, and then you'll be able to do better on the practice. Does that make sense? Yes.
So with February, February was related with Poseidon, and the Romans didn't like Poseidon because they were scared to sea because they had multiple ships.
Okay.
So that's why they didn't like February.
Superstition. All right, here we go. I said play.
The Earth, our spaceship.
No. Yes.
Welcome aboard for a one-year cruise around the sun. Yes, we do revolve around the sun, but not on a circle, on an ellipse. And it's now, during the first days of January, that we're closest to the sun. So why is the weather so cold? In fact, the difference between near the sun and far from the sun is insignificant. A there's a much more important reason. The Earth doesn't spin straight, but slightly askew. The axis isn't vertical, it's tilted on its orbit. So when the northern hemisphere tips into shadow, the nights are long, the days are short. But more importantly, because the Earth is tilted, the sun's rays reach us at different angles. In the tropics, a ray of sunlight hits the ground vertically. It's hot. But the same ray in the northern hemisphere arrives at an angle. Its energy is spread over a surface 3 times greater, providing 3 times less heat. We're cold. In the north, it's winter. In the south, it's summer. The tilt of the Earth's axis gives us the seasons. At this very moment, you're hurtling through space at 107,000 kilometers an hour. That's 30 kilometers every second. The Earth takes a year to go around the sun.
Wait, but that's not the same number
And along with the Earth, 8 other planets circle the sun, each on its own orbit.
So we were in miles per hour. They were mentioning it in kilometers per hour. So 61,200 probably equals about 107,000 kilometers per hour. We were in miles per hour.
On the orbit just next to ours is our neighbor, Venus. Venus travels faster than the Earth, overtaking us. It's the brightest planet, the one we see best. Sometimes in the evening, sometimes in the morning. Why in the morning? We see Venus to the right of the sun. Seen from the Earth, this is what happens in the morning. We're looking at the part of the sky where Venus is. It appears on the horizon well before the sun, while it's still dark and the sun is still below the horizon to the left. That's why, in this position, we see Venus in the morning, at dawn. As the Earth continues to turn, we see the sun. It lights up the sky until we can't see the stars or planets anymore. So we continue our voyage on board our planet Earth. On the next orbit to the left, the Earth has a faster moving neighbor, traveling at 125,000 kilometers per hour and overtaking us. This is Venus. We call it the morning star, but it's not a star, it's a planet. What's the difference between a planet and a star? They look the same. But the stars shine like our sun. The planets don't shine, they reflect the sun's light. They're part of our solar system and are near to us. The stars are very far away. We can't reach them. This is Sirius, next to Orion, one of the closest stars. Even such a close star is out of our reach. If our spaceship Earth left its orbit and headed out of the solar system towards Sirius at its normal cruising speed, we'd take 80,000 years to get there. While at the same pace, we'd reach Venus in just 16 days. 80,000 years for Sirius, 16 days for Venus. That's the difference between the far-off universe of stars and our solar system with its nearby planets.
I'm gonna make it due tomorrow.
We still got
You'll
answer them though, even when you converted it to formulas.
Right.
We still got different answer.
how far off?
They said 107.
7.
We got 98,481.
Okay.
So we're off by.
We're off by a little bit.
So are we doing both questions?
Yep, we're gonna do both. All right. I just assigned 3.5. Let me assign 3.4. It's not due till the end of the day tomorrow, folks. You probably have time to get one of them done in class. I'm not expecting. Read carefully, though. Read carefully.